Welcome to the lecture series on numerical methods, and in numerical methods we are discussing on interpolation. So, in the interpolation section we have discussed different operators. So, today we will discuss about this central difference formulas. First we will discuss about this Gauss backward difference interpolation formula, then Gauss forward difference formula. Then we will just go for Stirling central difference approximation and Bessel's central difference approximation with an example. So, in the last class also we have given little hints about the Gauss backward difference formula, where usually we are just using even differences of y0 and odd differences of y of minus half, where the formula for this Gauss backward difference formula is expressed in the form like yp or y of xp can be written as a0, y0, a1 delta y of minus half, a2 delta square y0, a3 delta q y of minus half. So, likewise, if you will just express this left hand side of y of xp as y of x0 plus p is here, then it can be expressed in the form of e to the power p of y0, which can be written as 1 plus delta whole to the power p of y0 here. And if we will write the right hand side expression here in the coefficient form like a1 delta y of minus half, it can be expressed as a1 delta e of minus half y0 here. Similarly, if we will express here a3 delta q y of minus half, it can also be expressed as a3 delta q e to the power minus half of y0 here. So, if you will just express in the coefficients as y0 here, then both the sides can be expressed as a operator here. So, operator means we can just express this left hand side in the form of 1 plus delta whole to the power p. This can be expressed as right hand side as a0 plus a1 delta e power minus half plus a2 delta square plus a3 e to the power minus half plus as in this form here. So, now we can just express delta e to the power minus half in the form of delta expansion here, and delta q e to the power minus half also in the form of like delta here. Then if you will just equate both the sides coefficients, then we can obtain the values for a0, a1, a2 and a3, and where we can just find the exact formula for Newton's, this is Gauss backward formula. So, if you will just expand 1 plus delta whole to the power p here as LHS side here. So, in the LH side we can just write 1 plus delta whole power p as your first will be 1, then p delta plus p del square by factorial 2. So, likewise we can just express. So, this will be like a p into p minus 1 here. So, like p into p minus 1 by factorial 2 del square here. So, likewise we can just express. And if we will just express this right hand side terms here, delta e to the power minus half in terms of like delta here, we can just express that one in the form e to the power half minus e to the power minus half, since already we have known that this central difference operator delta can be expressed as e power of half minus e power of minus half. And if we want to write this term delta e power of minus half here, we can just write e power of half minus e to the power minus half here into e to the power minus half. And if we want to express this one in the form of a capital delta here, so we can just write this term as e to the power half minus e to the power minus half into e to the power half into e to the power minus 1 here. So, this means that if you will just take the product here, we can just obtain e minus 1 here, and this one we can just write e to the power minus 1, which can be expressed in the form of like delta into 1 plus delta whole inverse, and which can be expressed as delta by 1 plus delta here. Similarly, we can just express rest of the terms like delta q e to the power minus half in this form of capital delta, then all other terms also it can be expressed. So, if you will just express all these terms, this can be represented in the form of like delta square can be expressed as delta square by 1 plus delta, delta q can be expressed as delta q by 1 plus delta whole square, and delta to the power 4 can be expressed as delta to the power 4 by 1 plus delta whole square, and delta to the power 5 e to the power minus half, it can be expressed as delta to the power 5 by 1 plus delta whole cube. So, if you will just put all these coefficients in both the sides, then we can just obtain a0 value as 1 there, and to obtain the values of remaining coefficients like a1, if we will just multiply 1 plus delta in both the sides, then we can just obtain this coefficients as in the form of 1 plus p plus 1 into delta plus p into p plus 1 by factorial 2 delta square. So, this will be the left hand side, and in the right hand side we can just put that one as, since a0 equals to 1 there. So, this can be expressed as 1 into 1 plus delta plus a1 delta square plus a2 delta q plus likewise. So, if you will just see here the complete expression for this Newton's backward difference formula can be written in the form like 1 plus p plus 1 delta plus p into p plus 1 by factorial 2 delta square. This equals to 1 into 1 plus delta plus a1 delta square plus a2 delta q. Likewise, we can just write, and if you will just multiply by this factor like 1 plus delta here, so we can just write this coefficient that as 1 plus p plus 1 delta, and this can be written as like both the sides, if you will just take common here like 1 plus p plus 1 delta here, and if you will just equate the coefficient of delta and delta square, we can just obtain a1 value as p here. Since if you can just see here like 1 into 1 plus delta, and this right hand side and left hand side it can just cancel it out, and we can just obtain these values a1 as p and a2 equals to like a permutation of p plus 1 2 there, and again multiplying like 1 plus delta whole square, then sum of these coefficients again we can just get it up as a3 and a4 there, where this a3 can be expressed as p plus 1 3 and a4 can be expressed as p plus 2 4. Proceeding in this manner, we can just obtain these coefficients for 2m minus 1 power and 2m there, and a 2m minus 1 can be expressed as, since we are just taking these differences here, p plus m 2m minus 1 minus p plus m minus 1 2m minus 2, this can be given as p plus m minus 1 2m minus 1 there, and a 2m can be represented as p plus m and 2m there for m equals to 1 2 3. Likewise, we can just consider these values. Finally, if you will just put all these coefficients a1 a2 a3, then we can just obtain this formula as in the form of yp equals to y0 plus p delta y of minus half plus p plus 1 2 delta square of y0. So, this will be the formula for Gauss backward difference formula, and if we are just going for this Gauss forward central difference formula, then we can just choose these coefficients as these forward marching steps. Like if you will just write these coefficients, that we can just write yp as a0 y0 a1 delta y of half a2 delta square y0 a3 delta q y of half. So, likewise we can just write where these coefficients a0 a1 a2 a3 are to be determined, and if you will just use this same relationship here, like this coefficient we can just replace here delta e to the power half of y0, and this coefficient it can be taken as delta q e to the power half of y0, So then we can just express both the sides in the form of like forward difference operator as the coefficients operated on y0 there. So if you will just write it in operator form, we can just write this left hand side that as 1 plus p delta plus p into p minus 1 by factorial 2 delta square plus p into p minus 1 into p minus 2 by 3 factorial delta q. This equals to a0 plus a1 delta plus a2 delta square by 1 plus delta, a3 delta q by 1 plus delta, a4 delta to the power 4 by 1 plus delta whole square plus up to like finite number of terms. If you will just compare these coefficients on both the sides like delta to the power 0 and delta to the power 1 here, then we can just obtain a0 as 1 and a1 as p. And if you will just multiply both the sides by 1 plus capital delta, then we can just obtain the values of a2 as the permutation of p2 and a3 as permutation of p plus 1 3 there. So likewise, if you will just multiply 1 by 1, we can obtain rest of the coefficients like a2m plus 1, and we can just write this Gauss forward formula as yp equals to y0 plus p delta y of half plus p plus 1 sorry p 2 here delta square of y0 plus p plus 1 3 delta q of y of half. So this one. So if we will take the average of these two schemes, then we can just obtain this Stirling central difference formula. This means that this formula uses y0 and its even differences plus average of the odd differences of y of minus half and y of half. Hence, the formula can be expressed in the form like yp equals to a0 y0 plus a1 mu delta y0, since we are just taking the average of this odd terms here. So that is why this mu operator is assigned in the odd terms here and even terms are remained in that scale only. So where these coefficients like a0, a1, a2, a3 are the constants to be determined, and mu is the average operator here, where mu can be expressed as e to the power half plus e to the power minus half by 2. If you will just express this one in constant coefficients form, then we can just obtain these values of a0 as 1 here, and rest of the coefficients will be expressed in the form of like a to m minus 1 as permutation of p plus m minus 1 by 2m minus 1, and a to m as half of like average terms we are just considering for this odd terms here. So that is why we can just consider p plus m 2m plus p plus m plus 1 2m, where m will vary from 1 to like finite number of terms. So if you will just expand these terms here, then we can just obtain these coefficients as a to m equals to p square into p square minus 1 square into p square minus 2 square up to p square minus m minus 1 whole square by 2m factorial here. So putting all these values, we can obtain this Stirling's central difference formula as yp equals to y0 plus p mu delta of y0 plus p square by 2 factorial delta square of y0 plus p plus 1 3 mu delta q of y0 plus p square into p square minus 1 square by 4 factorial delta to the power 4 y0 here, plus up to the finite number of terms, whatever these terms where we want to truncate the series. So up to that term we can just consider in the series expansion. So next we will just go for Bessel's central difference formula, where we will just use the opposite of this Stirling's formula. This means that we can just consider the average of odd differences is used in Stirling's formula, but here we can just use this average of the even differences. This means that in the a0 term, a2 term, a4 term, we can just use these average operators there. Hence, this formula can be represented in the form of y0 equals to a0 mu y of half plus a1 delta y of half plus a2 mu delta square y of half. So likewise we can just express and where these coefficients like A0, A1, A2, A3, A4 etc. are constants, and we can just determine by expanding both the series expansions, like if you will just consider like y of xp equals to as 1 plus delta whole to the power p, and we can just equate both the sides coefficients, then we can obtain the values for this A0, A1, A2, A3, A4 etc. So, if we want to expand this one, so we have to keep in mind that this average operators like mu e of half, it can be written in the form, since this term here we can just write mu e of half of y0, and this term also it can be written as mu delta square of e of half here. So, if we want to expand this term here, we can just write, since we are just operating mu operator on e to the power half here, so we can just write this one as e to the power half plus e to the power minus half by 2 into e to the power half here. Here also the same thing we can just use, since we are just using this operator on delta square e to the power half here. So, first we can just write this one as e to the power half plus e to the power minus half by 2 into your central difference operator delta square, sorry, this central difference operator delta square, then e to the power half here. So, if you will just multiply these terms here, first we will just get e then plus 1 by 2 here, and rest of the terms we can just equate and just equate with both the sides, and we can just obtain these coefficients that in the form of like delta e to the power half, it can be written as delta there, capital delta, and delta square can be written as delta square by 1 plus delta. Already we have discussed these things in the earlier slides, and delta to the power 4 can be expressed as delta to the power 4 by 1 plus delta whole square there. And if you will just put all these terms in terms of a capital delta here and equate both the sides, then we can just obtain these coefficients A0 as 1, A0 by 2 plus A1 as p. Then we can just get, since A0 is 1 there, so A1 can be computed as p minus half here, and if you will just multiply both the sides 1 plus capital delta throughout the equation and comparing the coefficients for delta square and delta q, we can just obtain p plus A2 as p into p plus 1 by 2 factorial, and A2 as the permutation of p plus 1 2 minus p1, this equals to permutation of p2. Similarly, we can just obtain this coefficients for A3 and A4. In general term, if you want to write A to m, that can be written as p plus m plus 1 to m there, and A to m plus 1, this can be written as permutation of p plus m minus 1 to m into p minus half by 2 m plus 1. And if we will just put all these coefficients and rewrite this formula, the formula can be written in the form of yp equals to mu y of half plus p minus half delta y of half plus p to mu delta square y of half. So, likewise we can just write. So, with these formulas we can just try to solve some of these problems, like for a defined example, it is just given that suppose the values of e to the power x are tabulated at different points starting from 1.00 to 2.0 with the incremental size 0.20, and it is asked to evaluate this value at 1.44 here. So, if we want to evaluate this value at 1.44, we have to consider this value along the center of the table here, since the tabular values are expressed as if you will just see. So, if we want to discuss about this central difference approximations, so we have to consider this value along the center of the table only. So, that is why the value it is asked here is 1.44, which is lying between 1.40 and 1.60 in the tabular values. So, if this is the value, then first we can just find this divided difference form here, like forward differences form. If you will just take the differences, so we can just find first difference, second difference, third difference, fourth difference and fifth difference here. Since the points are in the middle of the table, we will use this central difference formula like Stirling's formula or Bessel's formula here, And if you will just consider x equals to 1.44, by choosing x0 equals to 1.40 here, we can just obtain this values of p, that is form of like 1.44 minus 1.40 by 2.0, where this formula for p can be used as x equals to x naught plus ph, where x can be chosen as like 1.44 here, and from that formula itself we are just getting p as 0.2, and if you will just use this formula, we can just obtain this value as 4.22068, and especially if you will just see here, we are just using these values, that is a delta y of half plus delta y of minus half, since we are just using the central difference approximations. And in the central difference approximation, if you will just see that this average operator is operating on delta operator here, delta of y of half means it can just take the values of y1 minus y0, y of minus half means it can just take y0 minus y of minus 1, since the tabular values are associated like y of minus 3, y of minus 2, y of minus 1, y0, then y1, y2, y3. So, as I have discussed in the earlier classes, the similar fashion we can just choose these data values, and if you will just put in a proper form, then we can just use this forward difference table to get the central difference values here easily and in a comfortable form. Till now we have ended up all these formulations that formed by the central difference approximations, and we have solved the examples based on these central difference approximations also. In the next lecture we will just go for some other interpolation formulas to compute these functional values and the polynomial approximations. Thank you for listening this lecture.